I have no way of knowing if anyone actually can hear this. So again, apologies.
Yes, we can hear you.
I'm Adam Van Etten, data science and with satellite imagery and computer vision. I'll go ahead and skip the summary. You can read that on the website. So what's the motivation here? Well, we need to accelerate mapping. And so a good data point here is that after Hurricane Maria, took 70 plus days, over 2 months, to map Puerto Rico with just an army of volunteers. And this was something that obviously was impressive effort, but it's suboptimal if it takes this long. So if we can accelerate this, that would be obviously very beneficial. There's a ton of potential impacts of automated routing. I won't spend much time here, but it applies to other. And if we can do this in automated fashion, it's something that would benefit all these different communities. So a little more about the motivation of why we're doing this. So rapid extraction of road networks and key routes is critical in dynamic scenarios such as a disaster like Hurricane Maria. And kind of the elephant in the room is, well, can I already do routing with something like Google Maps or Bing or MapQuest, if you remember those days, are great options, right? But those data sets are often manually intensive. The data and the solutions are kind of proprietary quite often. They're often incomplete. And then if there is a dynamic event like a disaster, they're outdated, right? These neural networks are outdated. Like try doing optimized routing on airplane mode. It doesn't really work usually. So academic approaches, right? There's been a lot of research recently in this, which is pretty great, but those often are only a partial solution, right? So it's either just segmentation mask, like this middle image on the right, or if you do get road geometries and connections, it's only road just the geometry, not the properties. But road properties are crucial for true optimized routing. And here's an example why, right? Here's just a sample road network. And if you just do distance-based routing on the left, that's the route. But usually you care about time, right? How do you get from point A to point B in the fastest time? And that's what you see on the right there. It's a very, very different route. And that's something that is important to know, rather than just use this optimized time. OpenStreetMap is an amazing resource, something that I think a lot of people are very, very excited about, very supportive of, as are we. It is incomplete though. So, something like Google Maps is an option, but in open source, OpenStreetMaps, it has some gaps, right? So here's an OpenStreetMap example over Shanghai. And, max speed is a tag that you see, but 90% of the roads here have no max speed tag. So again, it's hard to do this optimized routing with open source solutions that exist currently as well. So how are we going to tackle this problem? Well, let's start with the data. Data we'll use is SpaceNet. This is a nonprofit collaboration run by Cosmic Works, where I work, but in collaboration with a bunch of other partners, really devoted to advancing foundational mapping. It's a pretty good data set, whole bunch of different cities. And then the newest addition is cities all over the globe. But we'll be focusing on kind of the roads piece. So I'll kind of skip on. There's two different types of foundational mapping labels. Building footprints is one, and then road network labels and features. So about 20,000 kilometers of roads have been manually labeled with features for 9 different geographic areas. To kind of drive interest in SpaceNet and show what the state of the art can be, have been 7 different challenges around the SpaceNet datasets. We here will focus on SpaceNets 3 and 5, which are the road datasets. And so this is looking at ultimately 4 different cities for 3, and then for 3 more for SpaceNet 5, so 8 different cities total, looking at road extraction and routing for those cities. So SpaceNet 5, what was SpaceNet 5? Well, the challenge here was to automatically extract roads just from satellite imagery and then get optimal route estimations with travel time projections. So on the left, you see an input image tile. And then In the middle here, this is a ground truth for a snapshot over Moscow. And then we want to categorize these roads, right? So get the network and also some different properties of the roads. So in brief, so what are the outputs? Well, we had, as with all space nets, we get a bunch of competitors' algorithms out. They're open sourced. And so that's pretty exciting. In this case, we'll be focusing on the baseline algorithm because it had comparable performance, but much faster inference time, so something's a little more deployable. So we call this CRESI, city scale road extraction from satellite imagery. And how does it work? And also note that this general approach was what all those winning algorithms also used for SpaceNet 5, right? Where the goal here is to let's extract the road network, but then also let's get speed estimates. How do we do it? Here's a schematic. We see the input tile here. It's fed into a segmentation algorithm, a multi-class segmentation algorithm where we differentiate by speed. And then we layer that together to get a road graph here. And then we can use these multiple channels to pull out the actual speed estimate for each road segment, which of course gives us a travel time. So it's a multi-step process, but we end up getting out, both the road network and then the property of the road. In this case, the property we care about is the travel time estimate slash the speed slash travel time estimate for each roadway. And then, of course, if you can't do this over large areas, it's not really very useful. So you can actually do a fairly simplistic approach to do this, scale to large areas. So we can do this on arbitrary scale quite quickly. Obviously, a city scale is the goal here, but you could extract it to as larger scales if you really desired. So how does it do? So here's an example. This is one of the test cities for SpaceNet 5, where there was no training done on this city whatsoever. It's just testing. This is actually Dar es Salaam. So here's a fairly large test image. And if you run this through the algorithm, right, the first step gives you a segmentation mask of roads. And right, this is where current analytics often stop, right? Here's your network prediction. Here's your prediction. All right, we're good. Moving on. That isn't very usable, right? So let's go one step further and let's pull out the actual road graph. Again, this is pretty useful. And this is where a lot of other algorithms stop, right? Let's get the road network graph, call it good. But if we really want something useful, all right, now let's color by road speed. So here in this case, right, yellow is slow and red is faster. And this is an actual road graph, that we started with nothing but the imagery. And then what we get is this road graph where we're projecting roads and their speeds. And we can use this, for optimized routing. And here's another shot that's kind of interesting. As if anything, machine learning is not perfect, but there are examples where we are able to kind of connect behind buildings, right? Which is obviously tricky, but important to do if you have an off-nadir shot, something that's not perfectly overhead. And so here's just comparing to kind of other options out there in the literature. So Road Tracer is a pretty cool algorithm that was put out a little bit ago to pull out roads. And if we just forget speed whatsoever, just look at the road networks and nothing but that. The road tracers on the left, and then our implementations on the right, we can see a significant improvement over the road tracer implementation. Even if we forget about speed, just look at the geometry and that's it. But then if we look at the speed as well, so this is a prediction here over Shanghai, we actually see the speed is actually extracted with very, very high fidelity. So won't go into too much detail here, but there's a very small gap between the length and the time metrics, which means that, again, doing a very good job of estimating speed for the roadways. So the hardest part is actually getting the network correct. But then with CRESI, we can get the speeds very, very well predicted once we get the network. Here's just a GIF of kind of building up the road network in Las Vegas for a test area. And you can see, right, it's doing a pretty good job of recognizing residential areas, which are yellow, slow speed limits, 25 miles an hour, and then building up to, red being highways. So Vegas is unsurprisingly an easy-ish city for a number of reasons we'll get to later. But again, this is doing a pretty good job of pulling out that road network, starting with nothing but imagery. So on to routing, right? This is kind of the whole premise originally of why we're doing this. And once we have this road network, we can extract a route. So starting in the red here, going to the green. But what's really interesting, right, is you can show that, again, kind of picking at random 2 points. On the left is what you would get if you just did typical routing that you get from algorithms now, which is the shortest length. But then on the right is actually incorporating the travel time information we pull out from this algorithm, and it's a very, very different route, right? So again, kind of underscores the importance of having this travel time estimation in your algorithm to get the optimal route. And this is something that, once you have this network, no matter what your starting point is, it's pretty quick to almost instantaneous, frankly, right, to calculate these optimal routes. So a few more things that I'll go into quickly. I know we started late, but a few lessons learned from SpaceNet 5. And the reason going into this is to kind of demonstrate how this approach actually it will apply to new scenarios. So the robustness of it is what's interesting. So what we're showing here are the scores for the top 5 competitors for SpaceNet 5, as well as the baseline on the far right for each different city. So there's 4 different cities, and then purple is total. And the kind of takeaway here, I know it's a lot to kind of process, is that red, which was the unseen city, no one had seen that before, is not appreciably lower in most submissions than the other cities. So what that means is that, when we train on basically 6 different cities, is what we did, then testing on a totally unseen geography, we actually have a model that's robust to new areas. That's pretty exciting. It means that these models actually have a chance to deploy. If there's a disaster, you can't pre-train on an area, you might still have a chance of having a model that's useful in a new unseen geography where you have to deploy it and get hopefully immediate results. There's also significant variation kind of in sea level predictions. And so we have these small different chips for scoring, which then we stitch together obviously for larger pictures. But even though the competitors had very similar scores, if I go back here, the purple line is all very similar. There's a huge variation in sea level predictions. And that's shown by the scatter here. And what that means is that neighborhood level details are far more important than broader things like, road widths, background color, lighting conditions that are kind of more city scale. So again, these kind of microscopic / neighborhood level features are actually very important for road networks. And surprisingly, you see a huge difference in scores depending on these factors. There's also, you can do a lot of correlation between features of roads, and I'll skip over this one a little bit. But what's interesting is here we're just doing a random forest fit based on a few features to our model, and what we see is that we actually have a very predictive model for given a certain set of features of only 6 different features. We do a very good job of predicting what the Apple score is. So Apple is how we're measuring road networks. The most predicted feature is the total length of the road in that scene, followed by max speed. So that's interesting in that, again, if you have an unseen area, you can easily compute these features like total meters, max speed, et cetera. You have a sense for how well you're actually predicting that road. That's good to know when you're going into unseen areas. So a few conclusions. We showed as open source methods can rapidly extract road networks directly from overhead imagery. We didn't talk too much about speed, but it's actually extremely fast. So we're getting, almost a square kilometer per minute, even on a CPU. We see that even for new locations, we're predicting road networks with quite high fidelity, and they can actually be, that's routable, right? You can actually route with these road networks. Travel time estimates are actually very accurate. And this combination of road networks, travel time, you can actually do optimized routing in unseen locations or in dynamic scenarios. So I will end there. And here's some information channels for people to peruse. Thank you.